Hello, everyone. Thank you all so much for clicking in and taking the time to learn about my research. My name is Li Yudong, and I work with Dr. Ling from Florida State University. I am very honored here to participate in this amazing event, the SAMPE University Research Symposium, for the second time as the finalist in the PhD category. I would like to present one of my research projects today in the mechanical and electrical property improvement of the double wall CNT composites from continuous water-assisted floating catalyst synthesis. I understand that most of you have never met me before, either in person or virtually, so I would like to take just a minute to share my background with you. I got my Bachelor of Science in Polymer Materials and Science from Beijing University of Chemical Technology in China, where I received extensive education covering applied mathematics, statistics, polymer science, biomedical, and chemical engineering. In 2015, I started my journey in the interdisciplinary PhD program in material science and engineering at Florida State University. And last month, I have successfully defended my PhD dissertation. Here's a list of my journal publications, conference papers, and some prizes and awards that I have won during the past few years. So when talking about improving the mechanical and electrical properties of the CNT composites, we have seen a lot of work focused on introducing bundle alignment or interface engineering. In other words, post-treatment or modifying the fabrication process. In this work, we try to trace all the way back to the very beginning of the problem. That is, we try to use an innovative approach to synthesize high-quality CNT. For the first part, we are going to go through the background, which led to the research motivation and our research goal. And we'll then investigate the effect of water concentration in the purity and morphology of as-produced CNTs. After that, we will further review the electrical and the mechanical property improvement of CNT BMI composites in order to demonstrate the effectiveness of the water-assisted FCCVD technique. And we'll wrap it up with a quick summary and suggested future work section. Since the discovery of CNTs in 1991, various synthesized processes were adopted, hoping to yield high-quality CNTs at a mass production level. Among them, there are three mainstream routes: arc discharge, laser ablation, and the CVD process. So the first two methods, arc discharge and laser ablation, heavily rely on the carbon sublimation or vaporization under high temperature. When I said high temperature, I'm talking about over 2,000, 3,000 Celsius. And which is why these two methods were proven to be impractical due to the high energy consumption and inefficiency. The conventional CVD process, on the other hand, it requires a remarkably lower temperature for the CNT to grow on a pre-deposited substrate. And this rationalizes wide application, especially on the laboratory scale. In early 2000s, a Japanese group took an innovative approach to introduce controlled amount of water vapor into the substrate-based CVD process. And they yielded single watt CNTs as shown in the CEM images here with over 99.8% purity. They believed that the water vapor served as a weak oxidizer and it selectively removed the amorphous carbon without actually damaging the CNT network. With a prolonged catalyst lifetime, this technique is anticipated to provide a simplified approach for achieving high purity CNT synthesis more efficiently. While the conventional substrate CVD process can tune the nanotube diameter by precisely controlling the catalyst sizes, The significant batch-to-batch variations remain a huge drawback for this process. On the other hand, with a continuous catalyst feed and controlled synthesized conditions within the reactor, the floating catalyst CVD, or we say FCCVD process, is definitely more suitable for mass production. And also it could achieve flexibility in the product form. For example, we can get yarns or sheets, as shown in the picture here, depending on how you would collect it. Although still somewhat controversial, one of the most widely accepted mechanism for it begins with the iron-containing precursor here, the ferrocene, decomposing at high temperature to release the iron atoms and forms nanoparticles of different sizes after interparticle collisions and agglomerations. Similarly, the sulfur atoms shown in red here were released from the thermal decomposition of thiophene. It bonds and coats the iron nanoparticles on the surface, which inhibits further catalyst particle growth. Until now, at stage C, we have a typical active catalyst particle for the CNT growth. Amorphous carbon, as shown in yellow here, is generally considered as a major byproduct in the hydrocarbon pyrolysis, and its deposition on the catalyst surface make them inactive. When we add water into the system, water selectively reacted with the amorphous carbon and remove the coating to revive the catalyst activity. And this will elevate the synthesized efficiency significantly. Additionally, smaller size CNTs could be achieved with the deionized water as a result of the catalyst size shrinkage. In this work, we have directly included the ionized water into the catalyst solution to provide a more homogeneous and uniform distribution. Based on the amount of water added into the standard catalyst solution, 3 groups were denoted as CNT0, CNT1, and CNT2 were investigated. Here in this slide, we are showing the in-house FCCVD setup for double watt CNT synthesis. So as you can see, we have an injection pump on the left to control the catalyst feeding rate, a commercial aluminum tube reactor, and on the other side, a rotating mandrel covered with Teflon sheet to serve as a sample holder. Here is a video showing the aerogel-like CNT socks being continuously collected. The stretching force from the rotating induce a mechanical stretch on the CNT bundles and slightly align them. And we'll talk more about this in the later sections. One of the most basic characterizations to assess CNT quality is thermogravimetric analysis, TGA. Here we're comparing the as-produced CNT from both the control group and the water-containing system. With increasing water concentration, the first derivative peak, showing in red here, shifted left to a lower temperature from 589 all the way to 574 Celsius. This indicates the increasing amount of higher curvature and the possibly smaller diameter CNT just because of their higher reactivity with oxygen. The second derivative peak occurred at approximately 650 to 660 Celsius. It referred to the oxidation of multi-watt CNTs as another component. With higher water concentration of CNT2 group, we saw 2 derivative weight peaks of similarly lower intensities. And this may suggest a transition to a more homogeneous CNT sizes and wall count distribution. We have also noticed a surprisingly increasing trend of catalyst residue from 18% all the way to 24%. The catalyst residue is the residue weight percentage at 800 Celsius. To better understand this trend, for CNT0 and CNT2 group, we took out samples during the TGA at 600, 700, and 800, and we examined those specimens using SEM and EDS. For the as-synthesized samples, the EDS results indicate a similar catalyst residue starting point at 10.55 and 10.54%, presumably due to the identical synthesized condition, except for the water concentration, of course. At 600, which is about 580 Celsius on the sample, the relative iron content of the CNT2 group has increased to over 20%, suggesting the initiation of carbon oxidation, which corresponds with the first derivative weight peak in the TGA curve. And that of the control group remained relatively constant at around 10%. This discrepancy was further magnified by 700 Celsius when the CNT2 group has accomplished the oxidation, and the oxidation of CNT0 group was not completed until 800 Celsius. So the earlier oxidation of the water-assisted CNT2 samples could be attributed to their smaller diameters, resulting from the removal of amorphous carbon layer on the catalyst nanoparticles before the CNT start to grow. Raman spectroscopy is a non-destructive chemical analysis technique based on the interaction of laser and the chemical bonds within the sample. So for carbon materials, our focuses are normally on the sp2 and sp3 hybridized carbon. At approximately 1580 per centimeter, the G band, we call it G band here, is characteristic of ordered graphitic structure, and it corresponds to the carbon atoms variation along the CNT axis. And the disorder induced the D band at around 1310 per centimeter. Indicates the relative amount of the defective impurities or other symmetry breaking defects. Especially in our case, we're talking about the amorphous carbon. Therefore, we use the intensity ratio of this two band Ig over Id as a direct measure of CNT quality. Under identical conditions, Ig and Id has increased by the addition of water from 7 all the way to over 10. And this CNT quality improvement could possibly be attributed to the effectiveness of catalyst cleaning by removing the amorphous carbon. We also note that the G band exhibited an asymmetric line shape with a weak peak appearing at 1590 per centimeter. This is likely associated with the large amount of multi-watt carbon nanotubes due to the diameter variations among different nanotubes. This asymmetric feature became less conspicuous as the water concentration increased, suggesting a narrower diameter distribution of multi-watt CNTs with fewer disorders. The internal structure of asphaltic CNTs were reviewed with high-resolution TEM in this slide. For the control group, the predominant component observed was multi-watt CNTs with a diameter measured from 19 to 23 nanometers. And double-watt CNTs start to emerge in the CNT1 group, accompanying some multi-watt CNTs with more than 10 walls on the side. With an even higher water concentration, the CNT2 group demonstrated a great majority of double-watt CNTs with the diameters ranging from 10 to 15 nanometers. These findings were in good agreement with the TGA analysis, where the derivative peak shift to lower temperature that we have mentioned earlier. By now, I believe that we have gained some understanding about the quality improvement of as-collected CNTs. As the microscopic CNT assemblies like sheets and yarns typically demonstrate much lower values in the mechanical and electrical measurements due to the impurities, the CNT discontinuity, and misalignment. We have manufactured the CNT BMI composites with these 3 different CNT samples through radon spraying and curing. To evaluate the mechanical properties, we performed tensile tests, and from the results showing here, we saw substantial difference between the axial and the transverse directions among all the groups. This could be explained by the stretching-induced alignment during collection. Along the alignment direction, the CNT0 and the CNT1 BMI composite demonstrated similar tensile strengths as shown in black here, at about 535 megapascal, and a 21% increment in tensile strength were observed from the CNT2 BMI composites. The Young's modulus, as shown in red here, of the water-containing composites were about 27 gigapascal, which was 16% higher than that of the control group. The improved mechanical properties could result from the decreased number of CNT walls and smaller diameters. Additionally, less amorphous carbon may have enhanced the CNT-BMI interface. To characterize the electrical conductivity, a 4-probe configuration was set as shown here. Similarly, we have seen substantial differences in the electrical conductivity when measured in the axial and the transverse direction. Once again, this indicates partial CNT alignment. We see that both the water-assisted groups, the CNT1 and CNT2 BMI composites, showing higher conductivity at around 1700 Siemens per centimeter. And this is about 16% increase when referenced to the control group. Here's a table summarizing the mechanical and electrical properties. Interestingly, both mechanical and electrical conductivity of CNT BMI composites exhibited a consistent anisotropy ratio around 3, which is presumably an indicator of the stretching-induced CNT alignment. To further study the mechanical properties of nanocomposites, we have conducted a nanoindentation test to review more detailed microstructure property relationships and also provide nanoscale insights of elastic modulus and indentation hardness. The as-collected CNTs were saturated in a BMI solution and then sandwiched in between the unidirectional carbon fiber prepreg before curing. I want to note here that the carbon fiber prepreg was designed to provide support because this is a cross-sectional test. From the result here, it is evident that the modulus increased significantly, probably 2 to 3 times when it's compared to the tensile Young's modulus that we talked about earlier. This is because the tensile properties are more sensitive to the load transfer between the CNT and the Rasen matrix compared to the compressive properties reflected in this nanoindentation test. Interestingly, the anisotropic ratio from the nanoindentation of CNT BMI composites was also around 3. This is very similar to what we have observed from the tensile and the electroconductivity measurements. So with the proposed water-assisted FCCVD process, we have achieved a continuous CNT synthesis and collection. And our hypothesis was that the addition of water selectively removed the amorphous carbon without damaging the CNT network, which yield a transition toward more double-wall CNTs with reduced diameters and improved qualities. The mechanical and electrical properties could be attributed to the water cleaning effect, and which led to the enhanced CNT quality and improved the CNT BMI interface. We observed a consistent anisotropic ratio around 3 for CNT BMI composites due to the stretching-induced bundle alignment. With all the information that we talked about, we believe that the proposed water-assisted FCCVD process has great potential to be applied in the mass production of high-quality CNTs. And what we have been working on is using this technique to fabricate thick components using the next generation CNT carbon composites. And as I have recently graduated, I personally think it will be an interesting direction to explore if we could add modeling or simulation work on the synthesis mechanism or the catalyst activity. For the for this last opportunity, I would like to acknowledge my advisor, Dr. Liang and Dr. Park, for all of their help and guidance throughout this journey. And I would like to acknowledge Air Force, NASA, and NSF for funding our research. And also all this amazing personnel from SAMPE North America. You guys are awesome, and I really, really appreciate that you have been making this happen for us. It means a lot. And I understand that we cannot do a live Q&A session like we normally do before COVID, like as a seminar or research symposium. But if you have any questions, comments, concerns, please feel free to email me at this address here, and I'll be more than happy to answer them. And thank you guys so much for the attention and for your time. I really appreciate, and I hope everyone stays safe. Thank you.